This video is a quick introduction to metal-ligand multiple bonds, and we're going to be looking at some examples of some oxo compounds, which has an O2- moiety, and nitrito compounds, which has an N3- ligand attached to it. First, we're going to consider this equilibrium between this dihydroxo tetraaqua compound and this oxo pentaaqua compound here, where you can conceptually think about this as just transferring this proton from this oxygen here to this oxygen here. Concerning this reaction, we can ask ourselves two questions. First question is, where does the equilibrium constant lie? Does it lie towards the dihydroxo or the oxo compound? And the second question that we can ask is, how many bonds should we be drawing between the oxygen and the metal? If that was a carbon and not a metal center, then you would put a double bond between the carbon and the oxygen. So we're going to ask ourselves, how many bonds should there be between that oxygen and the metal? And the answer to both of these questions is, it depends. Let's consider these three hypothetical metal complexes: the D8 nickel 2 complex, the D4 manganese 3 plus compound, and the D2 vanadium 3 plus compound. If we were to set up the equilibrium between these dihydroxo and the oxo complexes, we would draw the metal oxos as such, where we would place a single bond between the nickel and the oxygen for that D8 complex, a double bond between the manganese and the oxygen for the D4 complex, and a triple bond between the vanadium and the oxygen for the D2 complex. If we were to look at the equilibrium constants for these reactions, K here would be much, much less than 1. The equilibrium would lie strongly towards the dihydroxo compound. In contrast, for the vanadium species, K would be much larger than 1. The equilibrium lies over towards the oxo complex, with the equilibrium constant for this manganese species lying towards the oxo compound, but less so than in the case of the vanadium. These can be rationalized using simple ligand field arguments. So what we're going to do now is we're going to construct a modified ligand field diagram for a molybdenum nitrito compound and an osmium nitrito compound. By doing this, we'll see why early transition metals and transition metals with low DN counts form these metal-ligand multiple bonds. We're going to start by considering this molybdenum nitrito tetrachloro species. So this contains a molybdenum 6 plus ion, which is a D0 metal ion. Formerly it's Moly 4D0. What we're going to do is we're going to start looking at the molybdenum orbitals going from square planar D4H symmetry, and then add that axial nitrogen, bringing it into C4V symmetry. Drawing in the molybdenum fragment here, and the nitrogen there. We have the 5p orbitals, the 5p x and y, and the 5pz, the 5s, and then we have our 4d orbitals. The 4dx squared minus y squared, the 4dz squared, the 4dxy, and the 4D XZYZ. On this side, we're only going to consider the nitrogen 2p orbitals. The 2s is too low to effectively overlap with the atomic orbitals of a molybdenum, so it's going to come across as essentially non-bonding. So we have our 2px, 2py, and 2pz. In C4V symmetry, the dxy comes across as a non-bonding orbital, and the dx squared minus y squared will. This has B2 symmetry, and this has B1 symmetry. You're going to get overlap of the 2px and 2py with the 5px and 5py on molybdenum, as well as the degenerate 4DXZ, 4DYZ pair. So a modest elevation here. And here, we're going to strongly interact. With these, forming our E and E star orbitals. We're also going to get overlap of this 2pz with the 5s, the 5pz, and the 4dz squared, with the major interaction being with the 4dz squared. Forming your A1 and your A1 star. Placing electrons into these, we have this with these being the so-called metal d orbitals. We're now going to draw the molecular orbitals involved in bonding to the nitrito group. So the bonding orbitals are made up of your PZ, PX, and Py on the nitrogen, overlapping with the dz squared, the 3dxz, and the 3dyz. These are bonding orbitals, so they're in phase. Furthermore, these bonding orbitals are closer in energy to the nitrogen atomic orbitals, so they're dominated by the nitrogen. They have a huge amount of nitrito character. If we look, we see that the A1 is forming a sigma type bond, while your E's are forming pi bonds. The antibonding combinations are going to be out of phase, and they're going to be metal dominated. So there we have our P's, and then the dz squared for the A1, the dxz for the E, and the dyz for the other E type orbital. So this, if you notice, it's an anti-bonding sigma star, while these two orbitals here from the dxz and the dyz make up our pi star orbitals. The overall bond order for the molybdenum nitrogen bond is going to equal 1/2 number of bonding electrons comprising that bond minus the number of antibonding electrons. So it's 6 minus 0. So we have a bond order of 3. So here we have that triple bond, and the reason we draw that as a triple bond is because we have a bond order of 3 for that moly nitrogen bond. As we start to populate these E stars and this A1 star, the bond order will decrease and we draw fewer lines connecting that nitrogen and that molybdenum. This is the reason why compounds displaying metal-ligand multiple bonds contain metals that are either from the early transition metals or with low DN counts. It's because as you go to the late transition metals and higher DN counts, these become populated, you reduce your bond order, and therefore you have fewer bonds between that ligand and the metal. We're now going to go through and understand a little bit of the chemistry of some of these compounds that possess metal-ligand multiple bonds. And we're going to look at this osmium nitrito compound. This is an osmium 6+ nitrito species where we have this supporting tris-perazyl borate ligand. This is a D2 compound, and this will undergo an electrophilic attack of these boron species, for example, forming a nitrogen boron bond and also a nitrogen carbon bond. Upon doing this, the osmium center is formally reduced to an osmium 4+ species, so it now becomes D4. An experimental observation is that both of these compounds are diamagnetic. We're going to look at the osmium 6d orbitals and the nitrogen 2p orbitals, and we're going to start by placing this osmium species in nominal C4V symmetry with the nitrogen ligand coming down on top. So we're going to have our dx squared minus y squared, dz squared, dxy, dxz, dyz, and then the nitrogen 2p x and y and 2pz overlapping. That dxy comes across as non-bonding, as does the dx squared minus y squared coming across as non-bonding to that nitrogen. Strong interactions between the dxz and the dyz. And the dz squared and the 2pz. Going through, filling in electrons, 1, 2, 3, 4, 5, 6, and then the 2 electrons from the osmium D2 metal site. So what we have is that triple bond, because these antibonding orbitals that comprise the osmium-nitrogen interactions are unpopulated. So we have a triple bond. And just for completeness, I'm going to turn this to a Lewis structure, adding in the nitrogen 2s lone pair. That's non-bonding because it's deeply buried in energy. Now, this nitrito is electrophilic. So it can accept 2 electrons contained in that boron carbon bond in this BPH3 species, and we can form this moiety upon exposure to BPH3. When this occurs, the 2px and 2py orbitals are no longer available for bonding into the metal center. They're tied up in the nitrogen carbon and the nitrogen boron bond. So a way of thinking about it is that those 4 electrons from the 2px and the 2py are now incorporated in those 2 bonds. So the 2 electrons that were comprising the carbon boron bond in BPH3 are getting dumped into the metal d orbitals. Because these are no longer available for bonding, these dxz and dyz orbitals come down in energy because they're now non-bonding to that osmium center. The dxy remains non-bonding. The dx squared minus y squared remains non-bonding to the nitrogen, but the dz squared is still involved in bonding between that nitrogen and the osmium center. So because you only have 2 electrons in a sigma bonding orbital, no electrons in the sigma antibonding orbital, this remains a single bond. And as we go through, bringing the 2pz across, filling in electrons, 1, 2, for the 2 electrons being donated in to the osmium from the nitrogen. We have the d4, the 4 d electrons we have to deal with, which go in these orbitals here, generating that diamagnetic S = 0 singlet compound. We're now going to go back to these metal oxo compounds, looking at the vanadium oxo compound and the nickel oxo compound, and explain the chemistry that we've observed. So the vanadium oxo compound is a D2 compound. We can place 2 electrons in that 3dxy. We have no electrons in this pi star, no electrons in this sigma star, and so we can put 3 bonds between that vanadium and the oxygen. And just to complete the Lewis structure about the oxo, I'm going to place 2 electrons there for the oxygen 2s lone pair. For the D8, we still have those 2 electrons, but now we have this type of configuration. We can fill out lone pairs about that oxygen in a Lewis structure type sense, putting 2 electrons there and 2 electrons there. It's now relatively easy to rationalize why we have the equilibrium lying towards this dihydroxo species for the nickel compound, yet it lies towards the oxo for the vanadium compound. For the vanadium species, we have this triple bond here. We have no electrons occupying antibonding orbitals. It's rather stable. And if anything, will be electrophilic in nature. This oxo is not going to want to pick up protons unless there's accompanying electrons coming along with them. In contrast, this nickel oxo, which has the single bond between the nickel and the oxygen because we have 4 electrons in those pi star orbitals, is now electron rich. This oxo is going to be nucleophilic in nature. It's going to readily act as a base, picking up protons. Therefore, the equilibrium is going to lie far towards this species here. These arguments have been used to rationalize the so-called oxo-wall concept, which states that metal oxo compounds in tetragonal symmetry, so in nominal C4V symmetry, are not found in the cobalt group and to the right. You do find them in the iron group and to the left, or in other words, a wall exists between the iron and the cobalt group. With the iron group, you form metal oxo species. With the cobalt and later transition metals, you form metal hydroxo species. Because the corresponding oxo compound is unstable, it's nucleophilic, it's going to readily pick up a proton, forming the hydroxo species. As a really quick note, this applies to compounds with tetragonal symmetry. Once you go to symmetries where you do not have these fourfold rotational axes, the oxo-wall concept no longer applies.